Ok, benvenuti a tutti. Questo è il secondo seminario organizzato dal gruppo di comunicazione, dal gruppo di lavoro di comunicazione di ESB-ITA. È il primo seminario invece in cui vi presenteremo un tool e in particolare in questo caso vi presenteremo Deformetrica. Abbiamo tre speaker. Alessandra dal Politecnico di Torino, Sara dal Politecnico di Milano e Marilena da Fondazione Toscana Gabriele Monasterio. Vi ricordo che il seminario sarà registrato e disponibile sul nostro canale nuovo di YouTube. Trovate anche il primo seminario che abbiamo fatto il mese scorso già online sul canale. Lascio la parola ad Alessandra. Per le domande potremmo organizzarci, se avete domande durante le presentazioni potete scriverle nella chat così non ce le perdiamo. Le recuperiamo poi alla fine dei tre talk dove faremo una sessione più di discussione. I talk saranno in inglese, le domande le potete fare in italiano o in inglese come preferite, anche poi successivamente la discussione. Ok, prego Alessandra.
Ok, qua c'è la presentazione. Ok. Vedete il mio schermo, giusto?
Lo vediamo, non è ancora in
Sì,
modalità full.
dovrebbe farcela. Ok.
Perfetto, grazie.
Okay. So I will switch to English just to be consistent among all the presenters. So as Julia was mentioning, this will be a 3 voices presentation. I will start, and then Sara and Marilena will follow with some applications related to the cardiovascular field. I will present instead a little bit the software itself, so how it works, how we can use it. And in the meantime, I will also show to you some applications we worked on here in Politecnico. So to start, what is Deformetrica? Deformetrica is a software which can be downloaded for free, which can be used to perform statistical analysis about and for 2D and the 3D shapes. It basically works on a specific concept, which is the representation of shapes not in the Euclidean space, as we are mainly used to, but rather in a space represented by currents. And this allows Deformetrica to basically represent shapes inside a 2D or 3D ambient space, which is represented and which is defined by the so-called control points, which are the red dots you can see here for a 2D and for a 3D shapes. And this space is elastically transformed. And while elastically being transformed, this ambient space also brings with itself the shapes which are inside it. So in this case, a 2D or a 3D shape. And this is one of the most important and interesting points about Deformetrica because it allows great flexibility. So first of all, because it is this ambient space which is deformed, it brings whatever is inside it, which means that we can have shapes defined by landmarks, curves, surfaces, whatever we want. And the other very interesting point is that because of this, Deformetrica does not require correspondence between points in the shapes we want to analyze, which is often a requirement a little bit hard and cumbersome to obtain. What can we do with Deformetrica? Deformetrica foresees 3 main applications. The first one is registration, which means that if we have 2 shapes, Deformetrica is able to give us the elastic transformation to go from the first to the second. Then we can build we can perform an atlas construction, which means that if we give to Deformetrica as input a population of shapes, we will get the mean anatomical shape, of course computed based on the input shapes, plus a number of patient-specific anatomical features we will describe better later. And finally, the third application we can achieve with Deformetrica is geodesic regression, which involves time in the sense that given 2 input shapes, which represent an initial and a final configuration over time, Deformetrica is able to give us intermediate shape configurations at specific time points. Today, I will mainly focus on the atlas construction because this is the main application we worked on here. So I will start by giving an overview to you of what a deterministic atlas means. One of the main applications we could work on was the construction of a statistical shape model of the femur. So basically, we started from 93 proximal femur shapes, which came from 93 postmenopausal women. And we did know that some of these women fractured their femurs, while others did not. So our main interest was basically assessing if we could find a relationship between shape and fracture risk. And so the Deformetrica represented the first step in trying to achieve this objective. And particularly, we adopted the Deformetrica for the deterministic atlas construction. So what is a deterministic atlas? When the Deformetrica is asked to build a deterministic atlas, it will give a template, which is the mean anatomical shape computed over all the shapes we were given as an input. Here, the template is shown in blue, and it is superimposed just as an example to a patient-specific shape. And then together with the template, the Deformetrica also gives us of course, the grid of control points I was mentioning before, which defines this ambient space, which is elastically transformed, plus for each patient, a set of moment vectors, which are the black arrows we can see here in the picture. So these moment vectors are fundamental and crucial because they basically define the elastic transformation of the 3D ambient space. And this is very important because we get a set of moment vectors for each patient, which means that starting from the same template, so the mean anatomical shape, the moment vectors for each patient define how the template would have to be deformed in order to match the patient-specific shape of each subject we were given as input. And from this, it should be quite clear that these moment vectors are crucial because they do bring patient-specific anatomical information, okay? And therefore, using these mathematical formulations, we are able, starting from the template and from the moment vectors, to reconstruct each of our patient-specific shapes. So the general concept is that each shape can be seen as a template, as I was saying just now, deformed through this deformation function phi, and these deformation functions are functions of the moment vectors. And so simply by using these three very simple mathematical formulations, we eventually achieve the reconstruction. So our patient-specific shape taking the template plus the moment vectors. Okay, so how can we use the Deformetrica then? The Deformetrica does not work on Windows. It requires either Linux or Mac operating systems plus Anaconda. And the cool thing is that we only need this command line to run the Deformetrica and to run any of the main applications we can use. So to run a Deformetrica analysis, we need only 3 files, which are mentioned here: the model file, the dataset file, and the optimization parameter file, which are XML files, so simple text files. Now we are looking into these files a little bit better. So the model file is the core of the analysis because it is here that we declare what we want to do with the Deformetrica. So here, of course, we wanted to do a deterministic atlas. So you see that here we declared what kind of analysis we want to perform. Then we, of course, have to say the dimensions we will be working in, so 2D or 3D. In our case, we were in 3D. And then the kind of shape we are giving. In our cases, we had surface meshes, and so surface mesh was declared here. After, there are a number of user-defined input parameters. We can choose among different possibilities. And if we look into the Deformetrica documentation on internet, you'll find all the possibilities you have. Because these require to be defined by the user, we need to pay attention to these, and I will talk on this more in a few slides. Then there is the dataset file, which is quite simple and standard. So here we just need to declare where the shapes we are giving as input. So in our cases, we had a VTK file, so nodes, coordinates plus connectivity. So we just need to give for all of the subjects to be used, the path and the name of the file, of course. So it's just a list of all the data set to be used as input. And eventually, the optimization parameter is another file which contains a number of user-defined parameters which Deformetrica employs to run the optimization and therefore to run the overall analysis. So going back to the user-defined parameters I was mentioning before, here I highlighted the main ones, okay, which are contained both in the model file and in the optimization parameters file. In particular, the kernel width is quite important, okay? So Deformetrica employs kernel to go to the space, to go into the space defined by currents. And so this lambda, the kernel width, must be defined. Actually, Deformetrica employs two different kernels, which are used in two different sections of the model file. So the first kernel, which is employed and which is defined by the so-called lambda W, refers to how the shapes are represented. So the input shapes are represented, and therefore it also referred to the template computation. Here, lambda W defines, as can be seen very, very nicely in this picture from a paper in the literature, the resolution, the shapes which will be represented with. So you see that as we decrease lambda W, we get a much better resolution of our shapes. While lambda V, which is the kernel width which defines the other kernel, is related to the deformation of the template to match each patient-specific shape. In fact, this parameter affects the number of control points and therefore the number of moment vectors. And these parameters, of course, is related to the stiffness of the deformation. So as we lower lambda V, we make this deformation, this elastic transformation, to become less stiff. And this might be dangerous because we might get, as highlighted here, meaningless and unrealistic deformations. So we must be quite careful in defining these two numbers, the two kernel width, and to understand which are the optimal values for these numbers, but also for the other input user-defined input parameters, we need to perform a sensitivity analysis for sure. So the idea is that we change our input parameters, we run Deformetrica, so for each run of Deformetrica, we get a template and a set of moment vectors, and with these two pieces of information, as I was saying before, we can reconstruct each of our shapes. So at the end of the day, we can take our reconstructed shape, our input original shape, we can compare the two in terms, for example, of Euclidean distances, and eventually get an average reconstruction error. And of course, our objective would be to get moment vectors able to reconstruct a shape as close as possible to the original shape, which means that our sensitivity analysis must aim at the identification of the lowest average reconstruction error, okay? Here I reported a table which comes from one of our studies. As you see, we changed the lambda W and lambda V, and we could then identify the optimal combination of the two. And what did we do then? Well, we take our moment vectors and we put them into a matrix where the moment vectors are reported as X, Y, and Z components on each row, where each row is a patient. Okay, so we get as many rows as the number of patients we have, while in the columns we will have the moment vectors organized X, Y, Z coordinates. And this is our shape matrix. And now with this shape matrix, we can do a lot of stuff. And this is, I mean, a further analysis. In our case, it's because we were interested in building a statistical shape model. We employed both principal component analysis and partial least square analysis, which both, even though differently, allow us to get a statistical shape model, which can be represented like this. So we identify the modes, okay, which, for example, in the case of principal component analysis, represents the directions where the input information, so for in this case, the moment vectors, were most variable. So we could identify, said in other words, the most variable anatomical features of our femurs, okay? And here, just for an example, the first three modes, so the first three main anatomical features of our population are shown. And then we can also get the principal components, which are the projection of our original information on this mode. okay? This is again quite interesting because these principal components do represent for each mode where the patient locate on this shape feature, okay? So the weight basically of each patient along each mode. And in our case, we tried to use these principal components, which are actually patient-specific, to see if we could achieve a separation accurate enough between fracture and non-fracture cases, as we had this information available. And as you can see here quite clearly, we were quite sad to discover that shape was not that able to stratify and to separate our patients between fracture and non-fracture cases. So in this case, of course, we could employ principal components analysis or partially square also on a different matrix, not obtained with Deformetrica, but starting from a population of input shapes. In this case, as I was saying in my first slide, we would need isotopological meshes. So the great advantage Deformetrica brings in this context is that without any effort, we could get a consistent matrix in the sense that, of course, all the moment vectors were centered to the common grid of control points, and therefore we had the same number of moment vectors for each patient, and we could then easily put them in our shape matrix. Another application we have been working on recently, together with Bianca Griffo and the research group of Professor Umberto Morbiducci here in Politecnico, was something similar, but of course in a completely different field. So here the interest was basically on a cohort of diseased coronary arteries. And the idea was again to assess if we could identify shape features predictive of future myocardial infarction. So we had a number of lesions, of arteries which were culprit for myocardial infarction, other which were not. We employed again Deformetrica, of course, after our sensitivity analysis, we could achieve our shape matrix, and eventually we carried out a combined approach which involved the principal component analysis plus linear discriminant analysis. Here the idea is that we again obtain our statistical shape model, and then we employ the principal components to perform the linear discriminant analysis. Here you can have an overview of the results we got so far. Interestingly, we decided to use either the cohort as it was, so the original cohort, and then also to remove the main stenosis from these vessels, because we were interested in understanding if there were other features, of course the geometric features, not related to the stenosis itself, which could be predictive of the myocardial infarction. And as you can see here from the LDA results, we could see something very interesting, because if we look at the projection of our patients on this mode, so the mode identified with linear discriminant analysis, we found statistically significant differences between the patient-specific values for lesions, so for vessels culprit for myocardial infarction, and for vessels which were not. So also in this case, Deformetrica was very precious because we could achieve simply our shape matrix and then perform our analysis. So with this, I'm done, and I leave the floor to Sara. And I thank you very much for the attention, of course.
Thank you, Alessandra. Do you hear me my voice?
Yes.
Okay. Hello, everyone. I am Sara Barati. I'm a postdoc researcher in Politecnico di Milano, and I want to talk about our application of Deformetrica in our project. And thanks to Alessandra's comprehensive overview of Deformetrica and Atlas estimation, I want to talk more about registration and how we used it in thoracic aortic aneurysms. I want to first explain why we are doing this and what is the project. We are working on the digital twin for the treatment of thoracic aortic pathologies, which is a thoracic endovascular repair procedure. which includes putting in a stent graft inside a patient's thoracic aorta to uncover the lesion so the blood flow can go through the vessel without going into the pathology. We focus mainly on the thoracic aortic aneurysms, and we don't consider other lesions that need TEVAR. Like any other intervention, it can have some postoperative complications like endoleak, retrograde dissection, and device collapse. And what we do is providing high-fidelity deployment simulations to be able to evaluate these post-operative complications. The process starts from CT images of the patients, and then we do the reconstruction of the patient anatomy and discretization. And with the processes that the surgeon has chosen for this patient, we run the high-fidelity simulation of the deployment of the stent graft inside patient-specific model. This methodology has been validated and verified thoroughly by my colleagues. If you're interested, you can check this paper and other papers by the authors. As you can see, the results of the simulation and the post-operative CT images, the comparison between these two are really good, and the error is really small. So, like many other applications, we would prefer it to be automatic and have a faster workflow for different scenarios. So if we can compare different scenarios for each patient and see what we can do with it and what we can choose for the patient to be the best fit for that patient. So we want to use patient-specific simulations and post-processing results as an input for machine learning to be able to do surgery planning, choose optimal device for the patient, and do complication assessments. Like any other machine learning, it is important to consider that the quality of the predictions is heavily relying on the quality of the training population. And with the clinical data not being available that much, we need to consider a few things. First, we need to increase the number of training cases by virtual cohorts. We need to define faster reduced order simulations that is ideal for machine learning, and automatizing the process. So the registration that we use in Deformetrica comes from this idea. The process of the original validated simulation, from the moment that we have the CL file of the patient's anatomy until we have the post-deployed configuration of the stent graft, takes at least 5 or 6 hours. And it is not ideal if you want to use it for thousands of patient-specific cases to be used in machine learning training. So we had an idea to use the ideal geometry and start the simulation from the deployed device configuration in an ideal aorta, and then use Deformetrica for non-rigid registration between the ideal geometry to the patient-specific geometry. And then with that deformation, we apply the deformation to the ideal geometry with the stent graft inside it to find the deployed configuration of the stent graft in the patient-specific geometry. What it helps us with is that we only need to do this once for each device model, size, and landing zone combination. Landing zone is the place that the proximal part of the stent graft is going to be. And we don't need to do it for every patient-specific model, but for every new patient-specific model that we receive, we can just do the transformation or deformation simulation, which takes only a few minutes. For patient anatomies, we need to consider something. The variability in the geometric characteristics is really high. As you can see, the shape of the aorta, the angulation, the tortuosity, the position, the shape, and the size of the pathology is very different, and it can be in different places of the aorta. Also, one of the most important things is the placement of the supraannular branches. As you can see, they can be everywhere and the shape can be very different, and each of these can add multiple shape factors and shape features to our machine learning input, which is not ideal. So what we did as first, we considered the idealized geometry with branches, and then we saw that the number of the shape modes that we want to capture from the geometries of the patient models can be multiplied by a few numbers that we didn't want to consider. So we tried something. We considered cutting the branches, and instead of having the branches in the original geometry, we considered holes inside the ideal geometry. And then we ran the simulation, and we saw that the presence of the supraannular branches doesn't have that much effect on the final configuration of the stent graft, except for the places that there's a little bit of the stent graft ring that peeks into the branches. So what we considered next was using the ideal geometry with the holes in it. But when we went through the Deformetrica registration process, this is the patient, the first one, the blue one, is the patient geometry, and the white ones are the results from Deformetrica. This is the one with we did a sensitivity analysis to consider what is the best match for hyperparameters of the model, which are the lambda V and lambda W, which are the resolution and intensity of the deformation, as Alessandra explained. And we saw that if, in order to get a good agreement between the patient geometry and the final deformed geometry, we would need to consider many rounds of transformation, which is not ideal. And in the end, for example, consider that the patient's branches are here, and we have considered the holes up here. So the mesh would be stretched a lot to be able to conform to this pathology or the placement of the branches. So we considered something else. Instead of considering holes, we close the holes and we have a smooth surface for the idealized geometry. In this case, by removing the holes, we have removed the source of many instabilities inside the Deformetrica's registration process. So when we get a patient-specific model, the geometry of the patient, we cut the branches and we close the branches. So the only holes in this geometry would be the input and output, which the Deformetrica can actually support without much of instabilities, I would say. So for this, we have the idealized geometry and the patient-specific geometry. We use the Deformetrica's registration and some in-house optimization code to evaluate using the initial control points around the ideal geometry. We do multiple times the registration of the Deformetrica, and then measuring the error between the deformed geometry and the patient-specific geometry, we get the best fit for control points and momenta that give us the actually high fidelity geometry of the patient-specific model. And in the end, we use shooting module of Deformetrica, which gets the control points and the momenta to shoot the ideal geometry into the patient-specific geometry, which takes only a few minutes. We check this method for more complicated geometries, patient-specific geometries, to make sure that it works. We have the original patient anatomy and then the modified, which is cutting the branches and closing them. And then we used the Deformetrica's output as a boundary condition in finite element simulation. And as you can see, the agreement is fine. So by now we have the idea, we know that the idea works, but we need to see if it actually is in agreement with the high fidelity simulation and the city images. So we start using the deployed device in ideal geometry. We use non-rigid registration and we deploy the deformation to the patient model, to the ideal model, to get the patient-specific model of the final configuration of the stent graft. In order to compare them, in the top, you can see the final configuration of the stent graft with the high fidelity validated simulation that takes a few hours. And in the bottom, you see the final configuration of the stent graft with the simplified simulation, which takes only a few minutes. In order to compare them, we use the same method that we use for comparing the high fidelity simulation with CT images. We calculate the opening area and the circularity of the stent rings at peaks of each ring of the stent graft. And as you can see, the errors are very low. We have compared this with for multiple simulations, and we have gotten promising results. So for any patient specific anatomy, if we know the landing zone of the stent graft, we can do this simulation in just a few minutes from the original deployed device inside ideal geometry. So the other thing that we use the Deformetrica for, and I'm not gonna explain it thoroughly because Alessandra has already explained it, is a statistical shape modeling to create a virtual cohort. We choose desirable geometries. What is desirable geometry? The geometry that is representative of the majority of the patients that receive TWER. So the majority of patient cases are not this complicated. As you can see in the bottom image, there is a lot of angulation, a lot of tortuosity. The shape and the placement of the pathology is different, and it is not something that you see in the majority of the patient cases. So we focus on the ones that are the major category, I would say. And we use reliable, balanced, and standard distribution of these cases in our original patient-specific population, and use statistical shape modeling and deterministic atlas estimation of Deformetrica to create synthetic population, which is clinically relevant and anatomically plausible. So we check for these after creating the virtual population. But for the outliers, which are the complicated cases with a lot of different shape modes that we don't want to consider in our machine learning, we just use the original digital twin, which is the simulation. I just want to show you the way we do the virtual cohort estimation. After a few rounds of atlas estimation, we can, from the original ideal geometry and the control points, we can get the number of the control points, the position of the control points, and the mean shape that represents the mean of the patient-specific geometry. And then, after doing 3 rounds of atlas estimation and with the final template and control points, we also do the principal component analysis on the shape modes that we get from the original patient geometries. Calculating the cumulative variance, we choose the shape modes that capture 99% of the variance in shapes, and it gives us the opportunity to create more geometries with these shape modes. We first calculate the standard deviation of these shape modes, and then using Gaussian sampling, we define new momenta that can provide for us from the initial template geometry into the new geometries that we can use as new virtual patients. Then after that, we evaluate these virtual patients. You can create from different number of original patient geometries. You can create a few hundreds or even thousands of patient-specific virtual patient cases, but you need to be careful that the final cohort is compact and it has generalization, which means it should be actually representative of the original patient-specific cohort that you have used for this. I want to thank my colleagues in Politecnico di Milano and thank you for your attention. And I will leave the floor to Marilena.
Thank you, Sara. Okay, can you see my presentation?
Yes.
Okay, thank you. Good morning, everyone. I'm Marilena Mazzoli from Biocardiolab, Fondazione Monasterio, and today I'm going to present you the side effects of using Deformetrica. In literature, there are many statistical shape models of the thoracic aorta which use the Deformetrica to achieve the non-rigid registration of the dataset. However, these studies do not include the supraortic branches in their analysis because even though the Deformetrica succeeds in providing good registration for the aortic arch, it gives troubles when the supraortics are added. But these vessels play a key role in the mechanics of the aorta, so their inclusion into statistical shape model is highly desirable. There are therefore studies that attempt to include the supraortic vessel in their population study for statistical purposes. However, even in these cases, the non-rigid registration is only of the aortic arch, and the inclusion of the supraortic vessels is a posteriori via CAD. So the main question is, if we are interested in the supraortic vessels, is the Deformetrica the most suitable tool for our scope? When we approached the statistical shape model for the first time, we started with a dataset of 50 thoracic aortas from CT scans that were automatically segmented through a neural network. The shapes of the aortas differ greatly from each other because they included both healthy and aneurysmatic patients, with also different geometric types of aortic arch. In order to build a statistical shape model, two key steps are required: a preprocessing and an unrigid registration. Regarding the preprocessing, it wanted to homogenize the dataset in order to remove everything which is not considered as a shape, such as translations and rotations. First of all, we made a rigid alignment of all the target meshes on the template one through iterative closest point. We cut the edges in order to homogenize the lengths, and then with the clustering and remeshing, we tried to achieve roughly the same resolution on all the meshes. Then, for the non-rigid registration, we first tried Deformetrica, which is the most used tool for the non-rigid registration, and then we decided to write down our own algorithm. Deformetrica uses a set of control points to guide the registration. The initial position of the control points depends on the kernel width value sigma. Deformetrica initializes the control points to fill a box containing the source mesh, and so that the spacing between the control points is equal to the kernel width. As a result, the number of control points increases rapidly as the kernel width decreases. It is recommended to begin with larger values of sigma to produce smooth and global deformation, and then gradually decrease the sigma value to capture final details. However, the choice of this parameter can be challenging, and as can be seen from the videos below, if sigma's value is too small, too many features are picked up and noise dominates, whereas if sigma is too large, the function is overly smooth and important feature might be missed. So, here we can see how Deformetrica failed the registration when the supraortic vessels are included. We can see that the vessels are merged together and the holes did not correspond to their edges. And this is due to the fact that Deformetrica uses a single scale approach for the non-rigid registration. In order to overcome this issue, we developed our own algorithm, which is based on a second-order gradient descent approach, modified in order to simplify the second-order terms. We use the loss function based on the minimization of the chamfer distance and 4 steps of remeshing from 5,000 points to 25,000 points. We also introduce some landmarks at the boundaries in order to achieve the correct registration of the supraortic vessels and also of the ascending and the descending part of the aorta. Turning to the results, here are compared the registration of 3 target shapes represented in red, obtained with both Deformetrica and our algorithm. It can be seen how Deformetrica fails not only in identifying the supraortic vessels, but in some cases also for the descending aorta part. With a focus on our tool, this is the loss function during the multiscale non-rigid registration between the template geometry, which is represented in gray, and the random sample from the initial dataset, which is represented in red. In the animation below, we can see also the first steps of remeshing and therefore how the mesh resolution increases as the number of the iteration increases, while the loss function value decreases. The changes in slope of the loss function are due to the related changes in resolution. At this point, let me show you some application of our non-rigid registration algorithm. First of all, we registered the whole dataset of the 50 thoracic aorta, getting very satisfying registration not only on the aortic arch, but also on the supraortic vessels. We then tested our algorithm also in another very complex case of cardiovascular district, the pulmonary arteries affected by tetralogy of Fallot. Again, here the geometries of the vessels are very complex and differ greatly from each other, and those also from the template shape. In each of the previous two examples, we also took advantage of the registration to make data augmentation through the application of principal component analysis. In this way, it is possible to obtain also a larger number of novel realistic geometries. The principal component analysis is a process for the dimensionality reduction, which produces a new uncorrelated variable called modes, ordered by decreasing values of variance. This allowed us to go from 50 aortas made of 25,000 points and 40 pulmonary arteries of 6,000 points to 16 principal components, keeping almost the 98% of the variability within the dataset, which means that the mesh reconstruction is possible without significant losses. From the pictures below, we can see that by varying the different mode, the standard deviation of the different modes, novel realistic geometries are generated, and the geometrical variation is related to the amount of variance explained by the modes. Finally, this is a graphical representation that we developed. This allowed us to see how, by varying the standard deviation of different modes, it is possible to obtain new realistic geometries. And in particular, it is also possible to vary multiple modes simultaneously and generate random samples that combine different geometric variations together. And this was the last part of my presentation. Our tool is not open source yet, but we are open for collaboration. Thank you all for your attention.
Thank you. Thank you, all the speakers.